For those people that don't know, my name is Rachel Bray, and I'd like to wish a warm welcome to everybody this evening for the 4th edition of News from the Lab. We'll be looking at accelerators for society. I'm delighted to introduce tonight's speaker, Maurizio Vretenar, who is an accelerator physicist who joined CERN in 1988 to take part in the design, construction, and operation of linear accelerators. From 2008 to 2017, he was project leader for the construction of LINAC 4, the new injector for the CERN accelerator complex. Since 2013, he's engaged in a parallel activity as coordinator of large EU-supported projects for joint particle accelerator R&D, taking responsibility of EU CART 2, of ARES, and of the new innovation-oriented IFAST. In recent years, he's been increasingly active in the field of societal applications of accelerators, in particular in the medical field, where he's presently leading the Next Ion Medical Machine Study, NIMS, a new CERN initiative in the field of accelerators for cancer therapy with ions. I'm also very pleased to introduce you to this evening's moderator, Roxana Rata, who is a radiation protection physicist with a true interest in accelerator applications in the medical field. She did her PhD in radiation protection for proton therapy, and after that she joined CERN as a senior fellow in the RP group, working on the FCC project. After CERN, Roxana worked as an RP specialist for the British government, and 1 year ago, she joined Varian as a beam physics engineer for proton therapy systems. So tonight we'll have a 30-minute approximately talk by Maurizio, followed by 30 minutes of Q&A. And I think we're in for a real treat. Maurizio, the floor is yours.
Thank you very much, Rachel. Thank you very much. I start sharing the screen. I'm really excited at the idea of giving this seminar to the alumni, because we have such a wide range of experiences and expertise, and I'm really looking forward to your feedback. So basically, when we do accelerators for society, society is you. Not only you are the society, but also you have the expertise and the background to understand what we do and to give your comments. So I'm really looking forward to the discussion. But first of all, let's go for the seminar. And I will start with a simple message. Do you know how many particle accelerators there are in the world? More than 35,000. Something which is unbelievable, because when we think of accelerators, we always have in mind LHC, the large machines for science, but usually there are a lot of small machines doing everyday work in hospitals, in industries, for several applications, and this is really the bulk of accelerators. If you look at the numbers, only half of a percent of accelerators are working for particle physics, and only a bit more than 5% work for research. The others are about 1/3 for medical applications and 60% for industrial applications. So it's a large number of application of uses of accelerators. But why all that? What is so special with accelerators? Accelerators are our key to enter the subatomic world. It's the only tool that we have really to interact with the atoms, with the nuclei, for detection, so for observation, but also to interact with the matter. And this is something which is very special about accelerators. And this is only due to the fact that with accelerators, we can concentrate huge amounts of energy into very small volumes. So I always like the example of one proton out of the LHC, just a tiny proton. If you look at the energy of the proton, is almost nothing, 10 to the -6 joule. But if you look at the energy density, taking the classical radio of the proton, it's enormous. It's 10 to the power of 38 joules per cubic meter. So it's a huge way, a great way to concentrate energy into small volumes and then to interact with the atoms. Because when we send a particle beam to the matter, then what happens is that our particles will give energy to the cloud of electrons in the atom, creating proper ionization and other effects. And we can also come to giving energy to the nucleus, if we can penetrate to the nucleus and then interact with the nucleus itself. So a beam of accelerated particles is like a small knife that penetrates into the matter. It can produce ionization, breaking of chemical bonds, so act on the molecules, can produce secondary particles, photons or X-rays and neutrons, and can split and activate the nucleus. Is the dream of the ancient alchemists that it is realized thanks to particle accelerators. Energy can be delivered very precisely and even inside the matter. This is something which is very important to understand for accelerators, is that because of what is called the break peak. So if you send a beam of particles inside any type of matter, first of all, the beam will lose very slowly the energy. But at a certain moment, there will be a resonance between the energy of your particles and the dimension of the atoms that will give a lot of energy to the electrons and will deposit inside the matter. The distance depends on the energy that you can modulate. Thanks to the energy of our particle beam, you can distribute your energy. So this is what makes really accelerators unique, very different from lasers, for example. In lasers, you can also transmit very precisely a lot of energy, but it remains at the surface. With accelerators, you can go inside, and you can use accelerators to cure cancer, to kill bacteria, to treat materials, to dope semiconductors, and to produce secondary particles, intense streams of X-rays of other particles. So in particular, if we go to look at, now I will review the main applications of particle accelerators in general, and then I will tell you what we do at CERN and how we do it for accelerators for society. First of all, it is very important to understand that accelerators have a special role in medicine because there are several ways to interact with human tissues thanks to accelerators. Here you have a small cartoon. I try to change my pointer. Yes. Here you see a small cartoon. So you can send either your beam directly on tissues, and you can send protons, ions, electrons, or you can send X-rays created by a beam of electrons. And you see, for example, here the interaction that different types of particles have with the DNA. You see X-rays, protons, and ions that create a lot of double-strand breakings that are not repairable. You see that this is something that is useful. Of course, you can to cure cancer if this DNA is inside cancerous cells, but also can be used to kill bacteria, for example, with your radiation. Not only you can send on the on tissues primary beams or secondary beams, but you can also create radioisotopes. You can produce radioisotopes by interacting with the nucleus, and these radioisotopes can be injected into the body for imaging and for therapy. This is something that also we will see in the following of my seminar. What is interesting is that, so this is possible thanks to the Bragg peak, in particular for protons and ions, so you can modulate the way you penetrate into the body. And this is something that it's very important because basically accelerators allow to realize an old dream. Every technology starts from a dream. In this case, the dream is of bloodless surgery and imaging. So it's an old dream of humankind to be able to cure, to kill something inside the body, or even to see it inside of the body without opening it, without blood. And this is made possible by particle accelerators. But not only medicine is an important field for particle accelerators, there are also other important applications. Energy, so you all, I think, have heard of the accelerator-driven systems, or the energy amplifier, as it has been called. It's a very big field of feeding subcritical reactors with the particle accelerators. With particle accelerator, I don't want to enter into this field. There are some activities going on, but it is very complex. I should make a seminar in itself on it. But instead, I want to mention how much accelerators are used in the field of security, because thanks to X-rays, you can scan containers and materials. You can see here an example of a scanning using X-rays, but also you can produce neutrons to search for nuclear material. which is another important application of accelerators in the field of security. And then there are, of course, a lot of accelerators working in industry. These are all small accelerators, usually electron accelerators that reliably produce very intense fluxes of electrons that can be used for detection, for welding, for 3D sintering. For example, many 3D printers work with an electron beam. Sterilization is a very important field where you can use particle accelerators, and for treatment, for sterilization of seed and grains, but also polymer modification. Do you know that most of the foils that you use to wrap food at home are reinforced thanks to particle accelerators? So this is something that is used to reinforce the polymers. Then you can use accelerators to treat flue gas, working on the chemical bounds, wastewater, sewage, and going to ions. You could use accelerators, of course, for surface analysis, and you will have an example at the very end of my seminar, but also for ion implantation. Most of the semiconductors that are used in our electronics have been doped with an ion beam coming from a particle accelerator. So there are really a lot of applications. And I cannot go into the detail of all of this, but I want to make a warning that in fact one of the problems that we have in this field is the public perception of radiation. I was talking with some colleagues in Germany that have a system that treats with electrons, electron beam crops of different type before storage. And you see, you can adjust the energy of the electrons so that you kill the bacteria on the surface of the crops, but you don't enter into the crop. So there is absolutely no influence on the food. So no deterioration, for example, of the taste or the quality of the food. You just kill the bacteria. And people, they don't want of it. There are very many regulations that make difficult using this. And instead, everybody is using very dangerous, poisonous chemicals. Our crops are sterilized usually with chemicals that remain to the food chain, but often we are not allowed to use radiation for sterilization because of regulations, and because as soon as the consumer, the final users, know that has been sterilized with radiation, they don't want of it. Okay, but this was just a parenthesis. I don't want to open it. I want to go deeper into that, but this is something that we have to keep in mind, is something that often prevents the use of accelerators in society, in fact. Okay, but now let's go into a bit more detail in what is going on at CERN and what we do at CERN. I will first of all give a review of what we do in the field of medical accelerators for medicine, and then I will touch briefly at what we do for the environment. Not much, you will see, but quite interesting. And I will finish with artwork analysis with accelerators, just to give something to end in beauty this seminar. For medicine. So medicine is an important field for CERN, where there is always a lot of interest and support for activities for accelerators. The idea is that at CERN we have a huge portfolio of technologies with a potential impact on society and with a potential commercial interest to be used, for example, in medicine. And there is also support, for example, by the knowledge transfer group of CERN towards using these technologies for medicine. What is the problem? The problem is that our technologies at CERN have been developed for high energy, large accelerators for particle physics that, as they are of no interest for industry. So if I take an HC magnet, 14 meters, very high field, I give it to industry, there is no use for them. What they want, they tell, okay, now give me something small, very high field, bent magnets, working in pulsed mode. Yes, but it's something which is completely different from what we do from particle physics. So actually, we have a lot of technology at CERN, but they cannot be used or taken as they are. We need some preparatory work. So there is work that we have to do, first of all, at CERN, in collaborations, possibly already in contact with industry, to adapt our technologies for society. And this is what makes our work difficult at CERN. Work because at CERN, our mandate is restricted to particle physics. And there is not much support. There are very few resources for directed towards society applications. We only have some small funding, less than 0.5% of the CERN budget, 0.5 mil of the CERN budget, sorry, going to medical applications, but only to medical applications. And we have to find creative solutions to promote accelerator applications. Creative solutions means using a combination of some small funding from CERN as a seed money that is used to collect collaborations with other institutes, get support from European projects. Recently, we've been quite successful in getting funding for a few projects from the European Commission. And then now we're also starting to go to external funding and external partnership. So to go to collect external funding, which is also very difficult from CERN. Collecting money from donors at CERN is really very, very complicated. But okay, we will try. We are trying. So I will give you a review of project activities at CERN, but also I will tell you what is the creative solution that we are using to do it. And believe me, in the last year or so, I've spent more time in securing the funding and organizing the collaborations than in really doing the science. Luckily enough, you have a lot of young people doing the science, but okay, somebody's to take care of the coordination. But of course, we all work for a wider goal of highlighting the social benefit of technologies developed for high energy physics. So on this, everybody agrees that this is a priority for CERN and for us. So first example that I want to give you is treating cancer. Treating cancer with particle beams, which is now one of the priority. Small parenthesis, we also have to consider that, for example, so far in Europe, there have been almost 900,000 deaths because of COVID, but they have to be compared to almost 2 million deaths per year of cancer. So we all have in mind now the COVID emergency, but we should not forget that the real emergency is cancer in terms of numbers. Yes, and this is something that remains very high. Now, cancer treatment is relatively successful, but there is still a part of cancers, 10% of the cancers that are considered not curable. Usually are large, deep-seated, radio-resistant, and there is a lot of effort in going to treat these cancers. And the challenge is to treat them with radiation, depositing a lot of dose of radiation on the cancer and the minimum of the dose on the surrounding tissues to avoid secondary cancers, but also to improve the quality of life. Because often if we irradiate also the organs that are close to the tumor, the patient will probably survive from the tumor, but will have a very bad quality of life. So it is important also now not only to consider the cancer in terms of survival rate, but also of quality of life. And for this, the break peak is very helpful because usually cancers are treated with X-rays, with conventional radiation therapy, which is very effective for many cancers, but is less effective with others. And our particles, protons or ions, thanks to the very peculiar break peak that we don't have with the electrons of X-rays, allow to concentrate very precisely the dose on the cancer. So this is the general about radiation therapy with particles. What we have decided at CERN is that we are going to concentrate for the next few years on devising new accelerator systems to treat cancer with ions. Why? Because now proton therapy is commercial. There are already 4 vendors, 4 companies on the market that can provide proton therapy, and we don't want to go in competition with companies. They are much better than we are to make simpler and cheaper accelerators. Instead, what we want to do, we want to work on ion therapy, which is better than proton therapy in many respects. It is more precise, has a different effect on the cells because of the double-strand DNA breaking that is also effective against radiation-resistant tumors. And also there are very interesting results from recent tests of coupling ion therapy with immunotherapy that can open new avenues, for example, for the treatment of metastasis. So ion therapy is interesting, but so far there are very few accelerators providing therapy with the ions, in particular carbon ions. This is a typical ion for therapy. There are only 4 in Europe. 2 of them have been built following a design made at CERN at the end of the 90s. But now this design is already 20 years old. There's been a lot of progress in accelerator technology. And at CERN, we have started in 2019 the next ion medical machine study, which is a collaborative study with the goal of devising new designs for ion therapy accelerators that are smaller and less expensive than the present machines. Nowadays, it's almost 2,000 square meters that you need. It's huge, a machine for ion therapy, and you have to count about 200 million euros of cost of this facility, which is really something which is very highly affordable by healthcare providers, even in Europe. And to try to devise a next generation facility for ions, we have collected, you see, a large collaboration of many institutes. We have recently got support from 2 European projects, T3+ and IFAST, that have just started. And we have also an interesting prospective user of this facility, because we are collaborating with the CEIST, which is, I know, an almost impossible acronym, but it stands for Southeast Europe International Institute for Sustainable Technologies, which is an initiative which has been launched by a former CERN Director General Schopper with the idea of science for peace in the Southeast Europe, in the Balkan area, of starting a new common laboratory in a country of the West Balkans, including Bulgaria and Greece, which are also now part of this collaboration, and to build an international laboratory for cancer research and therapy with ion beams. And for us, the CEIST is a strategic partner, and the reference user would be the first user of the new NIMS design. Where do we go for NIMS? I don't want to go into too many technical details, but here you see that the secret is superconductivity. So if you want to make a smaller accelerator and possibly also less expensive, you have to go to superconductivity. But there is still quite a lot of work to do to convert, to adapt, let's say, the technologies, what we have learned thanks to DLHC and also to the DLHC upgrade in terms of superconducting magnets for the machines that are needed for ion therapy, in particular to build compact synchrotrons, as you see here, and compact gantries for distribution of the beam to the patients. But you see that, including shielding, we can come to imagining a machine that takes about 1,000 square meters, which is a factor of 2 with present facilities, and hopefully is also a factor of 2 in cost with present facilities. We're not looking only in this direction of superconducting synchrotrons. There's also some work going on at CERN on compact linear accelerators for ion therapy. Here you see a schematic drawing of a folded linear accelerator for cancer therapy, for carbon therapy, that you see here. So this is a facility based on this design, and you see how small here the accelerating structures are. And this is all technology that is derived from the click technology at 3 GHz. So these are derived from the competence and expertise of the click team, the CERN Linear Collider team. So this is something, and also we are working on the gantries, because something that the doctors, they want to be able to deliver the beam to the patients from different angles, and they want to change continuously the angles during the treatment, which means a huge structure to turn the beam around the patient. So far in Europe, there is only one of these gantries for carbon ions, which is installed in Heidelberg in Germany. And you see here how huge it is. This is a person, a man, observing the gantry. And this is because this is made with conventional resistive magnets. Now we are working on two alternative designs of gantries using superconducting magnets. One using superconducting cosine theta magnets, which are very similar to the standard, let's say, LHC type magnets, but they are mounted on a very light and very modern rotating device, which rotates around the patient that you see here. And then we are also working, so this is pursued in a big collaboration now with INFN of Italy, CNAO of Italy, sorry, it's a mistake, and Medaustron. And we hope that in 10 years, with their help and with the support of industry, we can already build such a superconducting gantry. Instead, a bit more long-term will be another very innovative idea. Instead of using a cosinus theta magnet, using a toroidal, a superconducting toroidal magnet, and instead of rotating the structure, the magnet, keep the magnet fixed and rotate the beam, in this case in 20 directions that are then focused on the patient. And work is going on for the moment only at CERN on this gatoroid design. And to finish my review of ion therapy, I will simply show a nice view, open view of how could appear the CEAST facility with the different research buildings. And here the roof is open to show the accelerator and the gantry, which is here, the superconducting rotating gantry. So this is something that also could hopefully be built in 10 years. The project has been submitted to the European Strategic Forum for Research Infrastructures, and CEAST is trying to get more political support and more support from the European Commission to get the priority as a priority research infrastructure for Europe over the next 10 years. All right. Now, but there are not only protons and ions for treatment of cancer. I'm very proud that at CERN there is also a group working on something which is very innovative, which is the so-called flash therapy. Recently, there's been a lot of enthusiasm on the idea of treating cancer with beams of electrons with very high doses given in a short time, which have been demonstrated are absorbed by the cancer, but are not absorbed by the healthy tissues. So it's a way, in the timing of the beam that actually there are different theories to understand how this happens, but nobody has really fully understood what happens. But the experimental evidence is that there is less absorption of the radiation by the healthy tissues, and this would give a nice way to spare the healthy tissues. And a group at CERN, which is led by Walter Wunsch, whom you see here in this picture, has started a collaboration with the Lausanne University Hospital to build the first prototype of a 100 MeV electron accelerator for flash therapy that should be installed at the hospital in Lausanne. And the accelerator is built fully using the X-band technology that has been developed for the CLIC project. You see an example here. So it's an interesting project because there is a wonderful partnership with the Lausanne Hospital. The Lausanne Hospital is now looking for funding. So there is already a design report prepared, and they are now looking for foundations and private donors to support the construction of the first prototype that could be installed already in 2023 and treat the first patient in 24-25. Flash, if successfully demonstrated on patients, could become, so there are still many problems to be solved, but could become another alternative way of treating cancer to conventional radiation therapy, protons and ions. So with a fourth way of treating cancers. All right. Something else that I want to mention is that we can also use accelerators for producing isotopes. This is an example of using a small radio frequency quadrupole. It's a small linear accelerator that we have built at CERN a few years ago, 5-6 years ago, to be used by a proton therapy system. This can also be used as a standalone system to be installed in hospitals to produce radioisotopes for imaging, in particular for radiation for PET scanning. It's a very small accelerator that you see here in this picture. This is one module of radio frequency quadrupole. We are also working on larger linear accelerator designs. This is something which is also very recent, a design of an accelerator of alpha particles that would be about 10 meters long and would allow to accelerate alpha particles at an energy sufficient to produce, for example, to produce isotopes like astatine 211, which can be used for targeted alpha therapy. This is a new technique that consists in sticking a radioisotopes emitting alphas. Alphas are very deadly, are very poisonous for the cells, but they have a very low penetration. So you have really to stick them into a targeting vector, which can an antibody, for example, and this can be done is radiochemistry. This can be injected into a patient, and this can accumulate in the cancer region and deliver its dose locally on the cancer. So at the moment, there are many clinical trials going on using alpha emitters, but we believe that at the moment when this will become a standard clinical practice, there will be a lot of demand for cheap and efficient accelerators for production of astatine and other alpha emitters, and we are preparing for that. Okay, I'm approaching the end of my seminar, and I have now two applications outside of medicine that I have to mention. So first of all, we have a little activity at CERN on environmental applications of accelerators, which is in connection to an idea of using electron accelerators for treating the exhausted from maritime traffic, from ships. People usually don't realize that the largest contributor to air pollution now is maritime traffic. Maritime traffic because it has exploded over the last years, first, and second because in high seas, the ships burn heavy fuel oil that is full of sulfur. Then also this is burned in diesel engines, and diesel produce a lot of nitrogen oxides and a lot of particulate. So there are now there are a lot of laws that are coming out to try to force ships to reduce pollution, at least in closed waters. Now it's already active in the Baltic, and there are now laws in preparation to protect the Mediterranean and also the American, the US coast. And a group of colleagues from Warsaw, in particular, have developed a system for treating the fumes, the smoke of a ship with a beam of electrons. This will act on the chemical bonds and will break the big oxide molecules of sulfur and nitrogen that then can be cleaned by simply a jet of water. So the smoke, before being emitted by the ship, goes through a stream of water, and which removes the rest. The system on paper is very efficient, and it's allowed an easy retrofit of existing ships. So it's been designed not as something to be installed on new ships, because there are other alternative systems to clean, to produce, to limit pollution, but it's a good way of mounting something in the funnel of the ship, of an existing ship, to reduce its pollution. And one of the nicest days of my career was when, in July 19, I went to the Riga shipyard in Latvia to assist, to be present to the first test of this system on a real ship that was an old Soviet-built tugboat, the Orkhons that you see here. I mean, old and rusty, was the perfect subject to test this technology, and the funnel was connected to this system that you see here, which is a mobile electron accelerator built by Fraunhofer Institute in Dresden, which is usually used for crops. And we had to complete the test in July before the harvesting season, when they had to go around to use this for treating crops. And the test was very successful, and the nitrogen removal rate was 45%, even in the poor conditions of this testing. That was a very nice example of coupling chip with a particular accelerator. And I finish with the art. I finish with the RFQ that you have seen, the radio frequency quadrupole that you have seen before in one of the pictures. We have designed this a few years ago for proton therapy, but now we are building a shorter version of this RFQ, only 1 meter, to be used for PIXI analysis, proton-induced X-ray emission. So this is something that is usually done in some laboratories with big electrostatic accelerators. We have a few MeV accelerator, and you can, for example, send a beam to an artwork. This is a portrait. If you send a beam, it's about 2 MeV of energy. It is enough energy for the Bragg peak to go beyond the layer of dust and grease that you have on the surface of a painting and go into the paint. So the energy, the Bragg peak is calibrated to deliver the energy inside the paint, and it produces X-rays. X-rays then can be analyzed by a spectrometer, and every chemical element has a specific signature on the X-ray spectrometry, and you can have the complete component, the chemical composition of the paint that has been used with the percentage very precisely of the different elements. This allows to see if the painting is fake or not. So was the paint really the one used at the time? But in particular, you can see previous restorations and treatments. You can make a kind of a history of the portrait. And this is now being built in collaboration with CERN, INFN, and the Italian Art Restoration Center, which is called the Opificio delle Pietre Dure in Florence, where this system will be installed. So we hope already end of next year that the system can be ready, tested in Florence, and installed in the Opificio to prepare the study for the restoration, to make a complete study of the different positions on the surface of the painting to prepare at the best the restoration work. But the system has been designed to be completely mobile, to be moved outside of the restoration center and go, for example, in churches to analyze frescoes or in small museums. Usually, directors of museums don't want to move the paintings. They prefer the accelerator to go to the museum. And this system is small and portable and can be used to do the examination in situ. Most of what we have seen in terms of accelerator designs is something which is, there's something in common. We have quite a lot of work to do towards the miniature accelerator. So what society needs, we believe, is a small accelerator, inexpensive, that can be used in different environments. And you've seen a few examples, our mini radio frequency quadrupole, the X-band structures of CLIC, and the superconducting synchrotron, the small LINAC. And it is something that we really want to do, keep working on how to make accelerators small, which is not so easy because at CERN we are very good in making big and expensive accelerators. To make them small and cheap, it's another story, but we are working on it. And I come now to my conclusions. So there is really a lot of work to innovate particle accelerators for science, and we want to couple these developments also with the developments for society. We are working on new technologies. Here you have had only a very quick overview. There are many other ideas, even more modern ideas of using lasers and plasmas to build small accelerators. We are following it with a lot of interest, and we are convinced that accelerators have a role in industry, in particular in the fourth industrial revolution that is just starting now, where we believe that accelerators have an important role to play. And I thank you for your attention.
Okay, thank you so much, Maurizio, for your talk. It was very interesting. As Rachel mentioned at the beginning of the session, we have 30 minutes for questions, discussions. So feel free to ask questions or write them in the chat, and Maurizio will answer every question.
At least I will try.
Well, this is your try, yes. No one?
Yes, I put a question in chat. I put a Q in chat. Elias. Okay, now just to say, Maurizio, yes, many thanks. Beautiful talk, very, very interesting. Concerning Flash, I'm not so aware of what happened, but you said that it's not completely understood why with the high energy and let's say in a very short time, you can kill the cancer, the tumors, but not the tissues. So how was this done? Who had the idea? I mean, why it was thought that this could work? Yes, just this process. Do you know more, Maurizio, about this?
Yes, what I can tell you what I know actually, that the idea is around since the 60s or the 70s. So it's an old idea that has been rediscovered or relaunched a few years ago, but some very successful testing on tissues, in particular in Orsay in France. And now this new revamping of the idea has started a lot of initiatives of testing Flash with electrons, with protons. About the mechanism, how it works, I was convinced that I knew why. I was convinced that this is related to depletion of oxygen in the cells, to the fact of how the cells treat oxygen, and to the fact that if you give the dose very quickly, you cannot really deplete all the oxygen. The oxygen cannot be stored in the cells. But only 2 weeks ago, I was following a very good lecture by a colleague from the KFZ, I think in Germany, who demonstrated that it is not the case. It is not true. So he was very convinced. They just published a paper. It's not the oxygen that is behind the flash effect. There are actually, he listed, I think, 7 or 8 theories to explain the flash effect. But he said that from his point of view, at the moment, there is not enough evidence to really believe, to demonstrate any of these theories. So I still believe that the oxygen has a role. I mean, I don't believe him 100%, but the debate is open in the community.
Okay, many thanks, Maurizio. Very, very interesting.
Hey, Michelle, please. You raised hand, or you have a question?
Thank you for your interest in the presentation. Concerning the militarization of the accelerator, have you taken in consideration to replace the magnet, hot or cold magnet, with crystals? Yes. This technology is called crystal channeling.
Yes. Okay. So what we do at CERN, I was talking about 10 years of time span. So we try to focus more on technologies that can have an application in the short, medium term. But crystal channeling is something that we are following. We see it is more for the longer term, and we want to apply it slowly. For example, now we've just started a thesis work on using crystals for extraction from the superconducting synchrotron. So this, I think, would be a very good initial application of crystals, not for the synchrotron yet, but at least for the extraction. So, and if it works on extraction, then we can go further. Yes.
But as far as you know, tests have been made also for to use the crystal as a quadrupole, focusing quadrupole and bending at 180 degrees.
Yes, and also I think that medical machines can be a good application of this technology because the beam is very low. I mean, in the RC you have a huge amount of beam, so you will burn your crystal, I think. But for the very small currents that you have in medical machines, this would be a very good application. Yes. So yes, we have this in mind. We didn't work on it yet. We want to start on slow extraction, but we have in mind that this might be very promising for medical accelerators.
Thank you.
Thank you.
Okay, we have another question in the chat from Adam. So what about a possibility to use antiproton beams for radiotherapy?
Oh yes, antiprotons are very expensive. This is the main problem. And if you want to have something small and cheap, it becomes really an issue. So antiprotons might be very effective. I think that there have been some tests of something has been published. I'm pretty sure about it. But what I know is that producing antiproton is so dirty and expensive, dirty in terms of radiation, that I don't see how they can be practically used.
Another question from Alberto related to the gatoroid. Is there any development ongoing also on the vector magnet?
Yes. In fact, the vector magnet, which is the magnet that distributes the beam, it's the critical point. And one of the critical points, the other is the beam optics. And the vector magnet might be a superconducting toroid, very similar to the other magnet, in fact. But actually, there is work going on the vector magnet. Yes.
There are no other questions, but I have one.
Yes.
So you said that CERN is planning to focus on ion
therapy.
an ion machine. Yeah, this will be only for carbons, or are you thinking at other types of ions as well?
Yes. No, good question. So at the moment, the reference is carbon, because also all the existing machines are working with carbon, and all the treatment protocols are for carbon. So you have to, the reference is carbon, but the designs that we're making is also for other type of ions, and every new facility that will make produce ion beams for therapy will have also a research part where one has to test and try a different type of ions. For example, helium is something that seems to have the good properties of ions with the easiness of production and of protons. Could be a good compromise between protons and carbon. But for the moment, we are only at the level of very limited in vitro studies, and much more research is needed for that.
Thank you. We have a comment from Thomas saying that neutral beam accelerators are important in plasma heating for fusion research.
Yes.
Yeah.
Can I add the comment?
Yes, please.
Thank you. I spend part of my life in working with accelerators, cyclotron, synchrotron for medical and industrial applications. And concerning SIGRUM, I would like to stress that the SIGRUM comes from the work made by a friend of mine, Pierluigi Riboni, who died recently. And I, together with Ugo Amaldi, I have written his obituary in the last issue of CERN Courier, and I mentioned SIGRUM. But another contribution to SIGRUM was given by a Greek company that, as I know, I have introduced to CERN. FEAC Engineering made the simulation of this gantry. So the connection and the technology transfer from this research to the industry this is an example of technology transfer. Yes.
Thank you. I'm glad that you mentioned this gantry, because in SIGRUM, the R at the end of SIGRUM stands for Riboni Unconventional Mechanics. Yes, and Pierluigi gave a great seminar a year and a half ago, I think, for us, where he presented his design. And SIGRUM is also a good example of how difficult it is to make these kind of things at CERN. Because now we are trying to, because I can get very little support from the CERN Magnet Group, which is over busy with High Lumen HC, and we are trying now to find different ways to keep the work going and to keep any type of contribution, including the Greek company that was involved in the magnet design, definitely.
It should be said that in this design, the gantry, the weight of the gantry is reduced to 20 tons, while in Heidelberg is 600 tons. So to rotate this large mass is problematic.
Yes.
We have spent at lunchtime with Pierluigi discussion, hours of discussion, making the design on paper, and then that is the conclusion. Unfortunately, he died and he cannot continue.
Yes. But we have other good mechanical engineers that are taking over, and okay, so the work is progressing, and there will be anyhow also some changes to these mechanics. Is going to also to advance.
Yeah, we have another question from Elias. How can we dream of treating cancers without any damage of the healthy tissue? Is flash the only possible solution?
Yes, we have already many solutions already: protons, ions, flash, and probably a combination of all of them.
Yes, but if I'm not mistaken, Maurizio, so X-rays, there is a large spectrum, you will damage. Then you have proton with the bright peak, but it's not a perfect also peak. I imagine there is some damage also.
Yes.
And then carbon, the peak seems to be even thinner. Now I don't remember, for the antiproton, is the peak even better, the bright peak, or?
I think it's even better, yes.
Yes.
But if I can comment on that, Elias, I think that the challenge now is not so much on the shape of the Bragg peak. The challenge is in how you align your patient on the machine, how you measure, you make a scanning just before treatment to be sure that you hit the organ, and also how you compensate for breathing, for example.
Yes.
So, and this is something that has much more impact than the width of the Bragg peak.
Okay, so you want to say that with proton or ions, if we have this peak like this, but then if we could have the patient not breathing, normally we want them to breathe, or we can compensate, etc., then we will really have almost 100% treatment without damaging the healthy tissues. So it's more this. It's more this the challenge.
Yes, no, but this I think is the challenge, and I think it is achievable, in fact. But it's not only or not specifically a challenge on the accelerator, because we always want to look at things in terms of like physicists. I mean, we like the Bragg peak, we want a sharp Bragg peak, and in fact, when you talk to physicians, the situation is completely different, because they think, I mean, on the fact how you move the patient, how you measure the patient. So the challenge is on both sides, let's say.
But what you say that from the accelerator side and with this Bragg peak, normally it seems to be fine. Now we have to progress there. But with flash, maybe we open even more. Maybe this is even better for this, or could be better in the future.
Yes. Because of the fact that you can not only that you have this effect of fast dose, it's the lower effect on the healthy tissues, but also that we learn how that we can give more dose in a shorter time, which is something that at the moment the doctors don't like. So I see. So if you look in the past, how cancer treatment was in the 60s, when you used the cobalt bombs for very, very, very dirty treatment, how far we went over the last 50 years. I can imagine that 50 years from now, I mean, we can really think that we can successfully treat many cancers.
Excellent. Many thanks, Maurizio.
Alberto, please.
Okay, thank you. I maybe have also a comment continuing on the question from before, and maybe if Maurizio, you can comment a bit also on theragnostics, or on the fact of bringing the radiation inside, and maybe that's linked also to the possibility of treating without passing through healthy tissue. Thanks.
Yes, theragnostics is, so I mentioned, for example, targeted alpha therapy, which is treating the cancer locally with a radioisotope. But if this radioisotope emits, for example, photons or electrons, this can be detected from the outside, and you can see exactly where your radiation emitters are. So you can couple the treatment with the scanning. So this is something that you can do with the isotopes, but also I can add to what Alberto says, the fact that there are also ideas of using multiple particle beams. First of all, for example, a beam of protons for scanning, and then the beam of ions for treatment. And this is a direction to go. Yes. So because really the challenge is not to deliver precisely the dose, but to be sure where the tumor is. Right.
Are there any other questions? Comments? So it's another question from Theo. Could we hope reduce accelerator size still further?
Yes, okay, so for the moment it's still a hope. For example, when I told Michele Barone that at CERN we work with a span of 10, 20 years. I mean, we don't work too much on the far future, we leave this to universities. But for example, there is a lot of work on laser plasma accelerators that could potentially give huge acceleration gradients, allow really to make very small, very compact accelerators, but there is still a long way to go. A long way to go to master this type of techniques is just sending the beam instead of in a vacuum chamber, send it in the plasma and excite inside the plasma strong electric field waves with a laser. So you see, it's very difficult to manage, and on the other hand, it is very difficult to have a reliable beam out of it. And I have the impression that medical applications will probably the last that will use this kind of new technologies, because this is where you want to be absolutely 100% sure of where your beam is, how much beam you have, and where your beam goes. So yes, there are ideas to reduce even further the accelerators. We are not yet there. Much more development is needed, and but there will be time until I believe the medical field can profit of these technologies. So my goal is that to have an accelerator in every kitchen, in every house, but there is still quite a long way to go to it.
Is Maurizio's answer also for Alberto? Alberto, what do you think? Do you want to add something else?
Yes, I was exactly wondering on this. What about the cost, size, and robustness optimization? Because often we tackle this in separate angles, but somehow, well, also from experience, I know that integration and robustness, reliability are really key. And so, if you try to reduce the size, you end up increasing cost, and so I think this is also a very interesting subject to tackle at the design stage. Yeah.
Yes. So because there is a big difference between accelerators for medicine, accelerators for science. Everything must be well known, and quality assurance is very important. For example, I know a person who is running a company building control systems, and he told me, for me it is very easy, it's a factor of 4. The cost of a control system for a medical accelerator is 4 times the cost of a control system for a scientific accelerator, which gives you a bit the idea of the difference in requirements in the two fields.
Rachel, please.
Yeah, thank you, Maurizio. Earlier on, at the beginning of your presentation, which was excellent, you talked about the dream. You started to talk about dreaming, and I wanted to know, in your dreams, what do you think, looking into the future, what other applications do you think we can imagine for accelerators in the future? If there's any that you think you can predict, perhaps.
Okay, so personally, I'm quite interested in neutron inspection, in neutron analysis. Very small accelerators producing neutrons for inspection, and neutrons can visualize organic materials, while X-rays can visualize metal. I mean, my dream is a bit the equivalent of an X-ray scanner built with a small accelerator with neutrons for to see organic materials. So this is an interesting application. And then there is many more. Maybe I can also do some advertising, because only this morning we had a meeting to discuss a future challenge-based innovation. We want in the summer of 2022 to invite at Archon near CERN some teams of young students, multidisciplinary from different disciplines, that would come and think of new possible applications of particle accelerators under the coaching of experts from CERN and from elsewhere. And by the way, if you have students who are interested, in January we were going to start the recruitment of the students for this innovation. This is funded by one of the European projects that I am running.
We can advertise that on the network.
Yeah.
So,
Good.
Yes.
Maurizio, just an information for you, since I'm collaborating also with the European Spallation Source, they will build a lot of beamline with neutrons to make organic inspection. So you may join us.
Yes. But the point is to be something portable. I mean, there's something small and portable. This is the challenge. I mean, we'll never have the same features than the ESS. But so if you have a small sample, you go to the ESS. But yeah, and you do. But if you have something big that you can't move, then this is where I think is the challenge to build a smaller, a portable ESS. I mean, would be the. I see Christine, who is.
Yeah, indeed, because this idea would be great. It's a dream as well, but the capacity is exactly what you were discussing. But I'll try to put it as well in the to-do list in terms of how we could improve the ESS, definitively. Yes. But thanks a lot for the talk. Wonderful presentation.
Thank you.
Okay, I think we don't have any other questions. Rachel, please.
Thank you. Many thanks to you, Maurizio, and also Roxana for a really highly appreciated presentation. You'll have to come back and give us another one and give us an update.
Yes.
In some time. Just to let everybody know, thank you so much for also your questions, your active participation. The recording is going to be made available, and I'm going to post it on the alumni.CERN platform. And if I may also advertise, the CERN Alumni Network will be celebrating its 4th anniversary next Tuesday. So to celebrate that, we're organising a LinkedIn Live. If you go to the CERN LinkedIn channel, you'll be able to see the live. And we're actually going to be featuring a company, a startup created by a CERN alumnus, who is also involved in the decarbonisation of the maritime industry. So it'll be interesting to see what types of methods he's using to do that. So I think all that remains is for me to say again, a big thank you to both Maurizio and Roxana. It's been super insightful and very, very well appreciated. And thank you to everybody else for taking part. And I'm going to put a little link into the chat. So if you'd be so kind as to fill out the survey so that we know what sort of events you'd like us to organise, what areas of CERN you'd like us to feature, and if you were pleased with the event, then please do let me know. So a very big thank you to everybody, and have a lovely sunny evening.
Thank you. You too.
Thank you.